Okay, to dive into module 17, now we're going to look at some more addition reactions of alkenes. Um, but these are going to be a little different in that they won't go through a carbocation intermediate. Okay, this should be a quick module. A lot of the same things that we talked about in module 16 will apply here, but the mechanism is going to look a little different. Um, Now, what if we assumed that the mechanism wasn't going to be that different and we wanted to make a prediction? Here I'm reacting an alkene with Br2. This would work with Cl2 or I2 actually. Um, so any of these halogens. Um, and if I think about what the best acceptor orbital on the BR-BR is, it's going to be sigma star BR-BR. It's one of my favorite orbitals to say because it rhymes. Um, and so if I were to make a prediction, I would think, okay, maybe pi CC is going to donate to sigma star BR-BR. So I'd have an arrow there. Um, and if I do that, I'm going to break that bromine-bromine bond. That's going to bond the bromine to one of the carbons. I have an arbitrary choice. I could bond it to the top carbon or the bottom carbon. It doesn't really make a difference. So I'll choose the top carbon. If I did that, it would leave a carbocation here on the bottom carbon. So now I know a carbocation is going to fall in love with the first nucleophile C's. In this case, that would be the Br minus that was just created. So that's going to come in and bond to the carbocation. So that would give me a product that looks like this. We have a name for this. We call this a vicinal dihalide. Vicinal is a term chemists mean to me to describe when two things are on neighboring carbons. So this would be called a vicinal dihalide because di meaning two, and halide because Br and Cl and I, those are halide atoms. So this would be known as a vicinal dihalide. So then my follow-up question here is, well, what would that indicate about the stereochemistry? Well, we saw this in the last module. If I make a carbocation, and I'm going to indicate my ring kind of with dotted lines here, and I make a carbocation and I have a bromine going up, um, let's say my bromine added to the top face of the molecule, so the bromine is going up. On my carbocation, I have an empty p orbital, and my additional bromide could attack from the top or the bottom, which means I should get a mix of syn and anti. We saw this in the last module. So I should get a mixture of products where the two have added to the same side and the products where the two have added to opposite sides. That's what this mechanism would predict. Turns out when you go into the lab and you run it, you only get one set of products. These two products are enantiomers, but notice they are both anti-additions. So when you run this reaction, you only get anti-addition, no syn addition. Okay, what that means is we need a new mechanism. When you get evidence that's inconsistent with your mechanism, you have to say, okay, our mechanism isn't correct, so we need to come up with a new one that can explain why we're seeing only anti-addition here. All right, so what might that new mechanism look like? Well, this is one where I wouldn't necessarily expect you to predict it. So I am going to show you what we've come up with as a possibility. So we had it right where pi cc is going to donate to sigma star CBR, or sorry, sigma star BRBR in this case. So these arrows were totally fine. But instead of making a carbocation, we're going to notice that bromine here has its own lone pair. And so instead of allowing a carbocation to get formed, that bromine is feeling generous. It says, hey, carbon, I don't want to leave you with an incomplete octet. So at the same time, this bromine lone pair is going to donate to pi star CC. All right. What is that going to do? Well, now I'm going to form not one, but two bonds from carbon to bromine. I'm going to form one bond from the pink arrow and one bond from the purple arrow. And they're both going to be bonded to the same bromine. Now that bromine, the second bromine is still broken off. That's still Br minus. But this bromine here that's forming this three-membered ring, this now has a positive formal charge. But the key is, it started out with 3 lone pairs. It still has 2 lone pairs. So it's got 2 bonds and 2 lone pairs. It's still fulfilling the octet rule, but it has a positive formal charge. And geometrically, if it's coming out, both of these bonds would be wedged. If it's going back into the page, both of them would be dashed. Okay. So now that I have this thing, we're going to call this a bromonium ion. It's a fun name. In general, for the various halogens, we would call these halonium ions. That's still a reactive species. It's not quite as unstable as a carbocation, but this is still unstable, and it will also bond with the first nucleophile it meets. In this case, that's going to be Br minus. The question is, which orbital is Br minus going to donate to? Well, it's going to have to donate to sigma star CBR. And so for this step, we'll have this bromine lone pair attacking sigma star CBR. Let's get an idea of the geometry of that. Again, I'm going to draw this bromonium ion, emphasizing these 3 atoms in a triangle. So if this is my bromonium ion, each of these carbons would have a hydrogen, and then there would be the ring kind of going off and around. Let's think about where, just going to redraw this hydrogen a little bit over here, redraw this one over here. If we think about where bromide is going to attack, if it's attacking sigma star CBR is going to lie over here. So when Br minus comes in to attack it, it needs to come from the opposite side of where the other bromine is. So when it makes its approach to sigma star CBr, it's got to be across from where the first bromine was. What that means is when we attack this new bromine is going to have to be pointed down if the old bromine is pointed up. Okay, so that gives us one of our products. That's this one. If we were to take this bromonium ion and attack the other carbon, because it's symmetric, there's no preference for one over the other, that would give us the other enantiomer. So this is a mechanism that explains why we get only anti-addition. We're going through a different intermediate called a bromonium ion. So that has some implications for reactions. Bromonium ions, they are reactive like carbocations, but not quite as reactive. So one consequence is that when you have a bromonium ion, it usually doesn't undergo alkyl shifts. So if I react this alkene at the bottom, if we reacted that with HBr, we would expect an alkyl shift, but reacting with Br2, we don't see an alkyl shift. The carbon chain stays as it is. 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. No alkyl shift. So that's one consequence. So there you have your second sort of class of mechanisms that you're introduced to in the class. These are mechanisms that go through helonium ions. We'll see more examples where we can apply this with other nucleophiles besides just the other halide ion coming in as a nucleophile. But the rest of this module is essentially revolving around that same idea.